Hello. 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 I'm waiting. I don't know if I'm waiting for the lights to dim or not. Oh, there you go. Oh. Is there anybody out there? So, welcome to this talk on refactoring to functional. I'll give my kind of like law of 2 feet, which is this is quite an introductory talk to functional programming. If you've done functional programming or if you're familiar with a lot of functional constructs, please feel free to leave. There's lots of other great talks going on at this time, so please, no worries from me. It's called the law of 2 feet. But since you all have the magnetic band, I do have people at the door scanning who leaves. So, not to hold any grudges or anything, I'm just saying. The other thing is, I'm all out of jokes, so I don't have any other jokes. So, that's it. No more funny stuff from me, I promise. Okay, so anyway, welcome to functional programming. I hope you've had a nice lunch. If there's anything you do know, feel free to fall asleep. I'll wake you up when I know there's something you don't know, which will be the last 3 minutes. Okay, so I will start with the definition. And when you start with a definition of something, you go to the ultimate source of truth, which is Wikipedia. And on Wikipedia, it says, in computer science, functional programming is a programming paradigm, a style of building the structure and elements of computer programs that treats computation as the evaluation of mathematical functions and avoids state and mutable data. It is declarative programming paradigm, which means programming is done with expressions. Fantastic. Other than saying that I read really well, what does that tell us? Not much. It does, however, highlight a few things. Which are the things, can anyone point them out? Which are the important things in that phrase, in that sentence? I'll give you a hint, they're in red, they're bold, right? So functions, avoid state and mutable data, be declarative and work with expressions, kind of thing. That's what it's saying. So let's go figure out why we have to do these things and become functional. So let's go ahead and refactor to functional. But before we do that, and this is a question that I ask myself a lot, why? You know, it's, have you all heard of the 5 whys? In Agile, they told you that when a customer asks for a feature, you say why? And they say, well, because I want it, and you're like, why? And you constantly ask this until they get annoyed and leave. Now, the idea is that you continuously ask this until you really get down to the reason of why they're doing something. It works great, and normally you get answers, unless you're talking to your children. Then it really sucks. You tell them not to do something, they're like, why? But important, I think, that everything we do is try and do it for a reason. So refactoring to functional, why should we refactor to functional? I just said in the keynote that we shouldn't listen to people that stand up on stage. But why should we do this? Well, I don't know about you, but my goals in writing software once I kind of graduated, which means about 3 years ago, and really got to understand software development, my goals started to become more apparent. One of them was to write less code. Because unless you're getting paid by the line of code, you really don't want to be spending most of your time writing a lot of code. Why? Because then you have to end up maintaining that code. So one of my goals has been to write less code. It's also been to write expressive code. Again, because writing code that is really smart and really fantastic and really makes you look clever, all it does is make you look clever for a little while. And then people get pissed off at you. And they say, this person just, you know, hates everyone, so they write very unexpressive code that others need to maintain. The added factor to this is, of course, that you yourself have to end up maintaining that code base eventually. So you might be clever today, you might not be so clever tomorrow. So we try and kind of write expressive code to try and express the intent of what we're doing as opposed to how we're doing it. Write correct code. Now, I've been doing software development for a long time, and when I first started, I didn't know what unit tests were. So I would just write code and ship it. Kind of, it was continuous delivery back then, it was called. And then my customers would ping me and say, this crashed, and I would say, okay, great, I'm at home. So, you know, I would write these code, and I would just ship these applications, and I want to really test them. And then someone said to me, look at this. It's called the unit test. And I said, wow, this is amazing. And then I started to write unit tests. And then I started to write more and more unit tests. And then someone said, right, you got a problem because you're just writing unit tests. You're not writing integration tests. I said, what's that? They said, when you got to combine all of these together. Like, okay, so I started to do permutations of them. And I ended up writing more tests than I've ever written code. And they said to me, it's a good thing. I said, okay, until things broke. I got to a point in my career where I was aiming for 100% code coverage. And then I woke up and I realized that this is not the great thing to do. In essence, now I'm at that kind of curve where I try and write as less tests as possible. So those that are really critical, those that express intent of the business, those that need to test things that other people haven't tested, I try and write. So my goal right now is not 100% code coverage. In fact, code coverage as a percentage is the wrong attitude to have ever. What this means is that the less code I write and the more correct code that someone else provides me, brilliant, I don't need to test it. And of course, write performant code. Why? Well, you already know about the silicon code valley syndrome. You know, we need to scale. No matter what we do, we need to scale. So those are our goals. Another goal, of course, is to be in the in crowd. So when we have conversations, we're kind of like the functional developer. And we know about functional programming, and we're not this old, antiquated, object-oriented people. Now, the next question is, can I use any language for this? I mean, can I write functional programming, or can I refactor to functional using any language? Well, the question then that we should ask ourselves is, what is a functional language? And that's kind of like, you know, asking a consultant, should I use this? They say, well, it depends. It's the same as, you know, it depends who you ask. They'll tell you a different definition of functional language. Let's just assume, and you can agree or disagree with me on this, but let's assume that a functional language needs to comply with a series of things. It needs to have functions as first-class citizens. Many believe, and I would somewhat as well, that the minimum thing for a language to be functional is to be able to build functions as building blocks. So they should be your primitive building blocks. Therefore, we need to have functions as first-class citizens. What this order means is that we need to have the ability to do higher-order functions. What are higher-order functions? Functions that take functions as parameters, or functions that return functions as parameters. Lambdas, because we want to write less code, so that is kind of convenient to use lambdas. And top-level functions, this is kind of with a little star. By top-level functions, I mean kind of like what you have in JavaScript. You know, in JavaScript, you can just write a function anywhere. In a file, you open a file, you write a function, and then you spend months looking for it. In normal language, well, in Java and C# and other languages, you can't have top-level functions. You have to place them inside a static object, a static class. Okay. Now, that's not really required, but it does sometimes make things a little bit more expressive. And the ability to have immutable data, and we'll see a little bit why this immutability is somewhat important in functional languages. Now, having said that, what will I be doing this talk in, and what code will you be seeing? I'm using a language which is called Kotlin, and the reason I'm using that is because for the past 2.5 years, that's kind of been my primary language. Most of the code that I'm writing right now is limited to Kotlin or JavaScript. And you can use any of these languages here, Java 8, Java 7, 5, plus a functional library, Scalar, JavaScript Closure, Haskell, F#, C#, OCaml, or Lisp, and the next language flavor of the month. And in essence, really, it doesn't matter. The important things are the constructs and the concepts. That's the main thing to take away from this talk. How do we do this in different languages? It's mostly a question of syntax. Okay. The other reason that is I find Kotlin a reasonably good language to work with and talk about is that it's simple. No, sorry, it's easy, let's say. If you've ever seen Rich Hickey's talk on simple made easy, there's a difference between easy and simple. Easy is something that you're accustomed to, something that you can relate to, something you've already seen. So as JavaScript, Java, C# developers, which most crowds that I speak to are, you'll find Kotlin very simple to pick up. But please, don't focus on the language or the syntax. Focus on the concepts, okay? So most of those, yes, Kotlin, Java 8, Scala, all of these are functional languages. JavaScript, again, as I say, if considered a language, then yes, it is functional. And that is, someone said, I'm picking too much on JavaScript. I said, OK, well, let's pick on PHP. Any PHP developers? Yeah, PHP is great as well. So just to get you up and running, very, very, very simple slide, just so that you see a little bit what the Kotlin syntax looks like. That's a basic function. It uses the Delphi approach where you have parameter string and returns a string. You have single line functions which take 2 parameters and return the sum of it, so often you don't even need to put a body in the function if it just returns the type. It's got type inference, so it allows it to be quite concise. Higher order function you can see on the 3rd line, and that's basically a function that takes a function. So here I have a function that takes an integer and returns an integer. That's how you declare a higher order function. And then at the last line, you have a Lambda expression. Okay? In Kotlin, you also have the ability to have top-level functions, so you don't have to wrap things inside classes. A few more examples of higher order functions and lambdas. So the top one is a sum, the next one is a multiply, and then I have a function called calculate, which takes 2 parameters of type integer and a function that takes 2 parameters and returns an integer. And then I can call that by doing calculate 2030. I can reference the function name by name. So the first one is just sum, then the second one is multiply. I can pass in my own lambda expression, and I can make a lambda expression more concise by using type inference. Okay? And that's really just enough for you to kind of get a feel for the syntax so that the later slides kind of make sense. So now let's talk a little bit about pure functions. What are pure functions? So the idea of a pure function is that I give some input, and I always provide the same output for that input. So anytime I give a function a 1, it will always produce the same value. And that's all it will do. It will just produce the same value, nothing else. What that means is there are no observable side effects. When that function is executed, nothing happens around it. So if you have a typical method in a class that when you invoke some variable, some private field is updated, that no longer is a pure function. And the reason that we want to try and aim for pure functions, one of the reasons that this has all come about, I mean, functional programming has been around for many, many years, about 45 years. It originated from lambda calculus. And in mathematics, basically everything has a single parameter, and they just want to reason about that function. You give it an input, it gives an output. It's much simpler to reason about when you don't have all of these different moving parts going around. So we try and aim for pure functions. That's also sometimes called referential transparency, which basically means that if I were to pull out that function and put in a table, a lookup table, it's exactly the same thing. So if a function has side effects, I can no longer do that, because I can do a lookup of values, but those things that it was causing as side effects won't be happening. So think of always pure functions as a lookup table. And the aim for that, as I said, is to reduce moving parts. That's what we try and do. If we have a function call, a method call, that every time we call it, 5 different things happen around us, it's harder for us to reason about. And it's harder for us to test because we've got to test all of these preconditions and postconditions. I want to write correct code. If I want to write correct code, I want to reason about the code I write easily and write as little unit tests as possible for that code. And please, take that with a quote, not literally. So we aim for pure functions. Now, having given this, can we achieve our goals? Okay? So let me show you a slide, and you tell me what it does. So you're looking at that slide, and you're trying to, anyone figured out what it does yet? It's a what? Instagram. Counts words. Okay, it does something. It says it at the top there. That's what it does. It does something. No, but seriously, look at that code, and now look at this code. Give me a whoa when you know what it does. Give me some sign. Oh, okay, a little whoa. That's kind of like I more or less know, right? Would you all agree that this one is easier to understand than this one? You have to say yes. Otherwise, this whole session will not make sense. So since I can't see you, I'll assume you're all saying yes, and don't say no. Okay? It does. It's more compact. It tells me what it does. Right? That's it. I can look at that code, and both functions being called it does something. I can reason about this code faster. It groups some elements. Okay, you don't know what it is. It is the same as Groovy, if you're familiar with Groovy. That's basically a Lambda expression. Group by is a Lambda expression. When a function in Kotlin has a single parameter, you can reference it by it. You don't have to be explicit. Having known that syntax, more or less you know what it does. A group buys an element, and then it maps that to a pair. Whereas this is a little bit more complicated to reason about. So you say, what's functional about that? Well, let's decompose that and figure out what exactly is functional about it and how we're refactoring to functional. Here's some loops and a list of albums, which is probably my favorite artist, Pink Floyd. And you have a list of albums, and you have the year and the position in which they hit the chart UK and the chart US. Now look at the code at the bottom, and what that is basically doing is getting the albums that were #1 hits in the US and the UK. So I'm creating an array list. I'm then looping through these elements. I'm checking to see if it was #1 in the UK and the US. If it is, I'm adding it to another list, and then I'm returning those elements. I have a lot of moving parts there. First of all, I have this looping thing, the iterator, the number, right? This index that I have to keep track of and make sure that I don't go out of bounds of that index. I want to start removing some things so that I can reason about this better and also write less code. So the first thing I'm going to do is remove some state. So all I've done here is add some syntax sugar, which basically says for albums. So now instead of having to worry about the index, I'm delegating that to the language, to the library, to what have you. Okay? But I'm still doing the same check. And then I'm still adding another album, etc. Add more syntax sugar. I've now moved from a loop, in which I write a single line of code, to an extension function, to a function which takes another function as a parameter. So already I've now introduced this concept of higher order function. I now have a function which is for each, which takes a Lambda expression, which is a higher order function. Okay? So nothing magical, nothing mystical. All I've done is just make it a function that takes another function. But the problem is that there's still a little bit of emphasis on the how, not the what. Right? I'm still emphasizing how I'm doing something as opposed to what I'm doing. Let's write less code. What I've just done now is take that same concept and create a new function. And I've called it filter, which does exactly the same thing. It just loops through elements, and then it finds all of the different things that match and returns it. So I've taken out the aspect of me having to deal with an additional list of elements that I have to add those elements in. That's it. That's already a refactoring to a functional approach, and it was nothing mind-blowing. It's just a filter function. That's it. So filter is a higher order function that takes another function. And that's what we try and aim for, just functions that take functions. Kind of making functions our building blocks. Now, we want to get the data in a specific way. This way we can't get it. Here's an example of how I could transform the data. I want to get data from one way to another. So I have a list of albums. Maybe I just want the years. So here is the top US and UK hits in number of years. So I do a filter, and now I get a years list. And on that years list, I go and add just the year. But again, I come back to this having a list of elements and then this for each, etc., and having to do this manually. Well, guess what? I can introduce another function for that, which is, again, a higher order function. It's called map. And map, all it does is take a collection of elements, do a transform on it, and give you back another collection of different elements. Now you can even have more involved samples. Here, for instance, I have my input is a list of lists. So I have a list of albums, and then that album in turn has a list of tracks. How would I do that? Again, I could go back to kind of more iterative approach and say, do a for each, and then on that get the album, and then filter the tracks, because in this case I want to get the albums and tracks lower than given number of seconds, and then add that to map that to another list, and then return the list. But again, I have that array list in there, Again, I have that for each in there, and again, I'm going back to have to deal with too many moving parts. And guess what? Just like we introduced filter, just like we introduced map, there's another function for that. It's called flat map, which, given a collection of collections, it transforms it to a collection. It flattens, basically, the list. Nothing earth-shattering about what we've done. Nothing. It's very, very simple. All I've done is just take functions that take functions as arguments. And that's the key thing. We're just using higher order functions and just passing parameters to them. So if we now put these two codes side by side, these do exactly the same thing. The only difference is that the bottom one is easier to reason about. Why? Because we're using functions as our primitive building blocks. Just like when you have 300 lines of code, you refactor that out into functions, here we're doing the same thing. The difference being that now we kind of embrace the idea of passing functions as parameters, as opposed to just types. That's it. Nothing more. So we can start to apply these techniques to common scenarios. So here's a typical scenario that, code that everyone has seen. It's called a customer filter, otherwise known as a repository pattern, which actually is wrong because repository patterns don't usually have search by methods or find by, but we do it nonetheless. So here I have a filter by name, which takes a list of customers and values, and then just checks to see if that customer is that value, and then adds it to a list, and then I've got a filter by country. If you look at those two pieces of code, they do exactly the same thing. Exactly. The only thing that changes is the condition. Instead of checking against name, I'm checking against country. Now, I could do a single function and pass in the field name by which I want to check, but that's kind of silly. Because now every time I want to enhance that with a new field, I've got to put a new case or a new if. Why don't I just use functions? So I could convert that into another function that just takes the actual condition that I want to check at. Reduce two functions down to one by just enabling higher order functions. Okay? Very simple, but starting to embrace this concept of functional programming. Now, how many of you here, probably some come from C#? Yes? No? In C#, yes. In C# we've had this for a very long time, except it wasn't called functional programming, and it wasn't called map or filter, etc. It was called select. It was called where. And it was a very great way for Eric Myers to introduce functional programming into C# without scaring us off. They just called it link. But it's exactly the same concept. Template pattern. You're all familiar with the template pattern, right? It's a pattern defined in object-oriented programming whereby if I have multiple classes doing more or less the same sequence of steps, but then each individual class somewhat varies, I can create a template. So here I have a customer record that persists some data, and when you want to edit a record, it does something, and then with the persistence, it does something, and I have an invoice which does the same thing, edits and persist data, and all of them, when they edit, they have to follow the same pattern. They first have to call check permissions, then they have to call edit record, then they have to call persist data. The only difference is how they do that. So I go ahead and I create an abstract class called record, and then I create a customer record, and then an invoice record, and for every type I create a new record, just to change what? The behavior of two functions. So how about I take that code and write it like this, that passes in two functions? Why am I creating all of those extra classes, all of those things, just for the fact of all I'm doing basically is changing behavior? That's all I'm doing, nothing more. If you are familiar with C#, you can do other things with functions. So in C# we have this thing which is kind of like a use with resources in Java, which is called a using statement, which basically says, I create an object, I do something with it, and then I have to dispose of it. It's an iDisposable. In Java, we have closable object. I do something with it, and I close it. We have to make sure that that takes place, right? We need to make sure that when we use that resource, eventually someone will call close. Why don't I use a function to do that? In fact, I could. I could create a function that takes an object, which is closable, and takes the actual body of the code that I want to execute. And then every time I call that function, I know that once that call has been completed, it will make sure it's closed the object. So now we start to add the ability to guarantee that things take place by using functions. Because we have the ability to start to move code around. We're passing code blocks, which is a great thing. We can even say when they take place. So if you're familiar with Go, Go has a defer method, which allows you to defer execution at some point. I could do that implementing it with a function. I say with defers. So here I say with defers, print line A, and then defer the execution of the line, print line deferred, and then print line B. And then I define the order and how that behaves by just embracing higher order functions. Okay? Strategy pattern is a common one that we find a lot in code bases. Again, I have, for instance, a sort algorithm, which is a trait, basically the same as an interface, and in fact now in Kotlin it is called an interface. And I have quick sort, and then I have bubble sort, and they're all basically the same thing. All the same thing. The only difference is how that code behaves. So effectively what we're doing is just creating a whole bunch of classes to change the behavior of some code. So we could do the same strategy, but just less code by passing in the function. Now, the question that arises when sometimes we talk about the strategy pattern, etc., is, okay, that is fine for when my class doesn't embrace state. What about if I need state? Now remember, if we're trying to refactor to functional, we're trying to move away from state. Why are we trying to move away from state? Because we're trying to eliminate moving parts. So there wouldn't be a direct mapping to mapping of a strategy pattern with state to passing functions as parameters. There would be a, how would I do this and avoid state? And if I do avoid state, then I have those pure functions that help me reason about them more easily. Here's another example, dependencies, right? When we talk about dependencies, you're all familiar with dependency injection, right? And you're all familiar with IOC containers. And here I have a customer repository that has data access passed in. And then I have, get by ID, get by name, get by email, and each of these in turn are going to use that dependency. But let's think a little bit about those dependencies, right? Here is a typical controller, and this could be Spring, it could be what have you. You've got your checkout controller, you've got whatever. And you start to pass in all of these dependencies. And you start to pass in 1, 2, 3, 4, 5, 6 dependencies, and at some point you're like, ooh, my number of dependencies have drastically grown. And then you know what happens? Someone turns around and says, IOC containers suck. Why? Well, because you can pass in as many dependencies as you want. Okay? Therefore, the IOC, the reasoning here is that if we allow developers, allow to easily just pass in dependencies to our classes, we stop thinking about these dependencies. And we end up with classes that have 5 or 6 dependencies passed in. We don't have to worry about the creation of it, because the IOC container will take care of it. Therefore, now we come up with really, really crappy code, which has like a whole bunch of dependencies inside the class, and what do? We blame the tool or the framework, which is great. We always do that. No, I don't think so. I don't necessarily think an IOC container sucks. I think that we should be aware of what we're doing. That's probably the main reason, right? Now, if you think about a class, what was the whole point of us doing dependency injection? What is the primary purpose? They've told us it's about decoupling. It's about decoupling one class from another. That's not true. It's about decoupling behavior. It's about decoupling the implementation. But it doesn't necessarily mean that it's decoupling things to classes. If we have a class that's passing in many dependencies, what we are doing is actually creating a tightly coupled class, right? That's it. We're just doing it in a different way. Instead of creating the dependencies internally and having this God class, now we're just doing it in a different way. But we're still creating a tightly coupled class. And we're depending on too many things. There's too much orchestration going around every time we want to do something. And a lot of this is actually enforced with frameworks. So if you look at, for example, I mean, in the .NET world, if you want to have, for instance, a customer controller, and basically on the URL do /customer/edit/customer/delete or what have you, everything has to go in this class called customer controller. And there's no other way around it unless you want to do mapping or manual mapping of routes, which kind of sucks. So we all stuff it in there, and then we end up with situations like this where we have 3 or 4 dependencies being passed in and a method using a single dependency. Right? Index uses its own, checkout uses its own, and there's no real synergy, there's no real coherence between all of these different dependencies. So maybe it's the way that we're abstracting the classes that's wrong when we're creating dependencies. So how do we deal with dependencies? Well, essentially we could actually pass in behavior. Again, maybe that abstraction, because normally when a class violates single responsibility because it's got too many dependencies passed in, maybe we need to raise that lower layer of abstraction or decouple it in a different way. So let's think a little bit functionally. Functions are our primitives, okay? They basically are primitives. And all we're basically doing is just combining functions. So all of the things that you've seen so far, which is filter, takes a predicate, map, takes a mapping function, group by, takes a key lookup function. All we're doing is just using functions, passing functions into functions, returning sometimes functions, and just using these, combining them. So here's an example of a function not returning a function, although it says on the title it does. It doesn't. That's just to make sure you're awake. So here I have an album, and I'm doing a filter by the year greater than 1976, and then I'm mapping those to a pair, and then I'm grouping it by the second. Very clear, very concise, very beautiful, right? We're pipelining these calls. Now, here's where things start to go wrong, because we need to also keep it readable. Okay? If we start to pipeline too many functions one after another, we can stop being able to easily reason about it. And then we go back to where we were. We go back to that first slide where we're looking through a loop, we're looking through moving parts, and we're not understanding what's happening. Now, you could, of course, do something like this, which is, create intermediate variables that say, okay, I've got the albums after a certain date, and then filter that, and then pass that to another value. But what you could also do is actually extract functions, right? If you have multiple functions that you're using over and over again, you can extract those and pass in another function to define the actual behavior. If we start to write code where we have tens of lines of functions, combined one after another, that doesn't necessarily mean we're achieving all of the goals that we set out to initially. I found this the other day on Twitter, right? This is by Roman Ilzarov, and he says, oh my God, this is now top contender for the sickest way to make simple code larger and slower. That is using basically higher order functions to implement the equals object. Now, I'm not going to say whether that's readable or not, you be the judge. I wouldn't find it that readable, but not. People can do many things with this. And as developers, you know what you can always trust us with? Screwing things up. So how do we reuse? If we have all of these functions and we have these primitive building blocks of functions, how do we reuse these functions all the time? So we can compose functions. Here, for instance, I have a function called sum and a function called squared, and all I want to do is compose them. I have a sum and a squared. Now, Kotlin doesn't have first-class composition. Pretty much the only language that has that is Haskell. But what I'm doing here is I've created a function that, guess what? It allows me to create composition of functions. And you can do this with pretty much any language. The idea here is I start to think of functions as my building blocks. And I want to be able to reuse these functions. I don't want to have to rewrite them all the time or call them all the time. So I could start to compose them. So the composition basically means that if I take a function that takes value A and returns B, and then I have another function that takes input parameter B and returns a C, I can compose the first one with the second one, thus resulting in taking a parameter A and returning a value C. And then I can do something like sum squared, which will take two parameters and then do the sum and the squared of those functions. There's another thing that you might come across when you're looking at functional programming, which is called currying. Now, what is curry? It's, Haskell Curry is the famous mathematician that this is named after. And currying basically, if you remember a while back, I said that in mathematics, where this has come, in lambda calculus, where this has originated, functions only take single parameters. So how do you transpose that to our world, where we have functions taking multiple parameters? That's where currying comes in. And currying, basically, what it does is take a function that takes 2 parameters or more and decomposes it into functions that take single parameters. So here I have a function called sum that takes 2 parameters, x and y. Sum curried, if I call curry on sum, what that's going to do is give me back a function, sum curried, which takes a single parameter. Now I can say sum curried 3, and what that is going to do is give me back a function that takes a single parameter onto which I pass the second parameter. You can think of this as the same way as calling a function with optional arguments. When you call a function with optional arguments, you prefix a set of arguments, and then you call that function. When you do so, it computes the results, and it returns the results to you. Currying is basically the same thing, except instead of calling the function, what it is doing is setting default parameters. In this case, you could use it to set default parameters, and then giving you back a function. Well, currying is actually decomposing, right? But that's what it could be used for. Here's another example. I have a sum curried of 3 parameters. So if I call curry once, it's going to give me back a function in which I can decompose it into single functions that take single parameters. And then that leads to what I was saying, which is now I can prefix certain parameters of a function and then just get back that function. Why is this useful? Again, if we're starting to treat functions as our primitive building blocks, and if a lot of times we keep calling the same function over and over again with the same parameter, we don't want to do this manually. We want to be able to use this. So we can create partial functions. Here, for example, I have a checkout handler, and that takes some behavior, and I can create a handler in my application that is called checkout handler partial card data. And what that basically means is that anytime someone calls checkout handler, it's going to, by default, use cart data. In my test, I can use the function without using that partial application of it. It's passing a default behavior in order to allow us to write less code and reuse things. Here's another example of a partial function. Here I have a sum with 2 parameters, and then I say sum number with 10, and that's going to give me sum partial 10. So now anytime I call that, it's going to take its first parameter, 10. So here if I call sum number with 10 on 5, it should give me back 15, because the first parameter is prefixed. But again, it's not invoking a function to get a result. It's invoking a function to get a function onto which you can then invoke, which is the main difference. And of course, beyond the actual functions, also what we have to deal with is data, because at the end of the day, that's all we do in our lives. You can call us what you want, you can say it's an art, you can say it's a craft, but all we're doing is taking data, processing it, and returning data. Kind of like whiskey, which is one of my favorite drinks, right? We start with water, barley, and we just generate magic. Okay? So what is our data? So we have customers, we have invoices, we have points, we have ages, we have different types of data. But normally it's kind of englobed in scalar values, which is like age, date of birth, and amount, or collections of abstract data types. So it could be list of customers, list of invoices, set of pairs, etc. And we can take as input lists, which we've been doing, and give output lists. Right? So common list operations, map, flat map, filter, find all, merge, zip. All of these things that we've just seen, right? And then sometimes we can obtain scalars from lists. So common scalar operations are first, last, find, aggregate. And if you're used to C# and LINQ, these all sound familiar. If you're used to SQL, these all sound familiar. And many of these functions, if you actually look at the implementation, they boil down to just a few number of functions, mainly being fold, reduce, etc. All of these, fold is kind of one of the primitives. And all of these basically do the same thing. They're just layers on top of layers. What is fold? Fold, when you first read about it, it feels like this weird, abstract thing. But it's actually a very simple concept. Here I have a collection of items, and I have a function. And I have this initial, the function takes two parameters, an x and a y. X is the accumulator, y is the element from the list. I call fold on it, and what it's going to do is going to take the first accumulator, first element of the list, produce another value. That value now becomes the first parameter. It becomes the accumulator. I call it again, call it again, call it again, so on and so forth, and eventually I end up with a single element. So all it's doing, fold, is just taking elements of the list with an accumulator and applying it until it comes out with a single value. Now, recursion, and we'll come back to fold, recursion is also something quite often used when we're talking about functional programming and functions. So here's a simple example of the recursive maximum. I have calculate the maximum of a list. I have a 0, so if it's 0 elements in the list, it says you cannot operate on an empty list. If it's a single element, it returns that value. If it is more than a single element, then it's going to return the maximum between the list and the maximum of the tail of that list. This is very common if you're studying like schema or a Lisp. If you've seen that, you always operate in terms of first element and rest of the elements. So this is a typical way of calculating the maximum. You know how else you can calculate a maximum? You can use fold, what we just saw, because it's essentially the same thing, except the first base element is called a 0. So you could implement a maximum of a list using fold, and it's much faster because it's not recursive. And reduce is exactly the same as fold, except the first parameter is 0 if it's with an integer or what have you. Now, another aspect is the immutability of the data. Why is that important? Again, this is all about reducing moving parts. If I don't mutate things, I don't have to worry about them. So it also allows us to do certain things. So if we try to treat lists as infinite, it allows for lazy evaluation. It allows for reactive programming, which is the next talk after this. And if you aim for immutability, basically what you're doing is you're creating things and not modifying them. Now, if you've all heard of domain-driven design and things like this, a lot of times they say, you know, I've created a customer object. How do I validate that customer object? Well, you have a method on it called validate. No, that's wrong. You should start to think that a customer object can only exist as a customer, although in DDD it wouldn't be a customer, it would be a customer in sales or what have you, could only exist, it can only exist if it's valid. So one aspect that we do often is create classes that only have read-only fields, thus allowing us or disallowing us from modifying something that's already been created. So that's why often you see talks about how domain-driven design fits in well with functional programming. It's this aspect of thinking about immutability of data. Now, one of the things that you always think about when you start to work with functional programming and recursive programming and stuff like that is performance. And here's the thing. By and large, performance has zero impact on your code because it's either the database or the internet connection or your server or something that probably has a greater impact than performance. But hey, let's think about it a little bit nonetheless. I hate Fibonacci. Here's the annoying Fibonacci, which I said was not in this talk. Well, I lied. So you all know Fibonacci. N equals 0 or n equals 1, return the number, else return Fibonacci recursive of n minus 1 and n minus 2. If you run that with about 20 or 30, you can go have a coffee, have a shower, watch some TV, come back, and it probably still hasn't finished. After a certain number, Fibonacci becomes really slow. Why does it become slow? Because it's recalculating the values over and over again. On each iteration, it's recalculating values. If you do the iterative approach, it's immediate. But hey, this is less readable than the previous one. If I didn't name it Fibonacci, you would have to look up what exactly it's doing. Reason about it longer. Now, in functional programming, there's this concept called memoization, which basically says, hey, if we're saying that functions are pure, and basically it's a lookup table, why don't we just use a cache, right? Why don't we just, every time we call something with a value, why don't we cache it? And a lot of languages, such as Haskell compilers, do the actual caching. Many functional languages don't. Well, many languages that allow for functional programming don't. Kotlin doesn't. But here's a very naive implementation of caching for Fibonacci, which basically says if I've invoked that function for a specific value, then just look it up in the cache. Don't recompute it. And it's still recursive. Still recursive. Now, if you do this, and you compare this with the iterative approach, it's not noticeable by eyesight. They go both as fast. Okay? So there are techniques in order to allow us to optimize recursion with this. There's also this concept of tail call in recursion, where we have, for example, a number, and then a recursive tail call means that the last function that's ever been called, the last thing on that function is calling the function itself. In this case, it's not. It's calling another function. It's called multiply. Right? Now, when a function is tail recursive, compilers can do optimizations and basically replace the recursion with tail call. So you can also take functions that are recursive and convert them into tail call recursive. So here's how you can convert a factorial to tail call recursive. And in the case of Kotlin, it doesn't do that. It doesn't do it automatically. You add an annotation, and then it will do tail call optimization. And compilers, again, also have a lot of techniques for trying to improve in terms of performance so that you don't worry about the call stack. A lot of times they can just inline functions that don't, again, have any side effects. They can basically inline that. Now, what about all those scary stuff? So probably you came to this talk and saying, oh, I'm going to learn about monads and monoids and endofunctors and category theories and all of those. No, I didn't actually mention any of that. And why didn't I mention that? When I started to look at functional programming, I got scared. I normally do. And I'm like, category theory. You have to know category theory. You have to know what an endofunctor is. You have to know what a functor is, of course. If you want to know what an endofunctor is, you need to know what an functor is or what morphisms are. Or what a monoid is, or a monad, and all of these words that I've tried to avoid. And I got a little bit of a pushback, and I'm like, oh, I really don't have time for all of this. And I found that, you know, actually, if you look at it and you forget all of that stuff momentarily, why would I want to learn functional programming? What value would it bring me? And I concentrated on the value, which is basically the result of this talk. Certain things allowing us to write more concise, more expressive, somewhat correct code. And then once you get onto that, once I got onto that, I started to learn now, how does this tie in with category theory? What is a category? How is it related to lambda calculus? What exactly is a monad, which I'm sure you've heard the term of a monad is a monoid in the category of endofunctors. And you're like, okay, well, great, fantastic, whatever that means. A functor actually is basically, you have a collection A, and then you can apply a function and then returns a collection B. Now, in category theory, that would be having a category and then returning another. Map somewhat is an example of a functor, but we haven't even brought that concept of functors up. But we've been using it. We've been using these concepts. Monads basically is an abstract data type that follows a series of conditions. And there are examples of monads in a sense. There's the option, if you're familiar with Scalar. There's a list monad or IEnumerable in C#. There's state monads. Now, why is even monad important? Why every time we talk about functional programming is this concept of monad? So one of the key functional programming languages by excellence is Haskell. Right? And Haskell consists basically of pure functions. In fact, Haskell is so pure that it's useless. You cannot print hello world in Haskell, because if you do, there is a side effect. You cannot throw an exception in Haskell, because if you do, there's a side effect. So when they were, you know, they write this programming language, it's fantastic, you can use it for reasoning, it's really great, it's got awesome pattern matching, awesome function declarations, it's brilliant, and it really is. I really like Haskell. But you're like, okay, now what do we do with this? Right. Now, the key with Haskell and the key with pure functions is to not have side effects. So they introduced this thing in Haskell called the monad with the idea of allowing side effects, but in a controlled way. And then being able to then chain these side effects, right? So that I can now have a side effect that does something to the output, and then I get a brand new state. Every time I apply a side effect, I get a brand new state, because remember, things should be immutable. And now I've got that state, and then I can apply something else to it and get something else. Thus, allowing for side effects, but at the same time, keeping with the pure essence of functional programming. But point is that, all of these concepts you have to learn, and I highly recommend that you learn. I still learn, we're all learning, and it's very important to learn. But these shouldn't be barriers or showstoppers in us adopting things, because first of all, we need to see the reasons for adopting things and what value it brings us. And then we can start to dive deeper. And we shouldn't be put off by these things such as category theory or monads, etc. So in summary, the idea here is basically to embrace functions as primitive elements. Start to think of functions as your building blocks. Just like you do with objects, classes, think of functions as building blocks. Focus on writing less your own code, because none of the things that we've seen is magic. A filter is implemented under the covers by library or by the language itself. Map, the same. For each, all of these are all implementations. The difference is that it's something someone else has written, tested, and we don't need to worry about. Right? What is the key aspect of it being functional? Well, they're higher order functions. They're functions that allow us to take functions as parameters. Focus on writing more descriptive code. And again, here we can go wrong. If we start to, abuse functional programming, we can end up with 50 calls chained one after another and then lose sight of what we set out to do initially. We now have, again, unreadable code. Right? What was the point? If it was to be more expressive and more correct and easier to reason about, let's not go down the path of doing it wrong. And already, if you look out, you can look out on GitHub, you can look out anywhere, and you can see that there's a lot of code out there that just doesn't make sense anymore, because somewhat abusing this concept of chaining function calls. Focus on writing deterministic code. Code that I know basically does what it's meant to do and focuses on that, and again, limit the number of kind of things that I don't necessarily need to test because the code is somewhat deterministic. And again, don't quote on that. There's a place and a time for unit tests, and I still unit test, and although personally I favor more integration tests over unit tests. I'm not saying that we should stop unit testing, but let's not waste time unit testing the wrong things. And really, at least from the perspective here, and probably you've known a lot of it, you can see that it's absolutely not rocket science, and we shouldn't shy away from this aspect of functional code. So some books that I recommend, there's a very good book called The Little Schemer, which is a version of The Little Lisper, which basically as a story shows you how to create from step one all the different constructs that we use, based on the concept of CDR and cars, which is head and tail of a list. Learn your Haskell. Even if you're never going to use Haskell in your life, I highly recommend you learn it. It gives a lot of good perspective on things. And there's a website called learnyourhaskell.com, which if you want to read it online, it's absolutely free. Then you can contribute by paying for the book and downloading it. And for the Java crowd, there's a book by Venkat, a great book which is called Functional Programming in Java, which shows you a lot of the things that we've seen here in a little bit more detail and how to use them with Java 8 with the new features of Lambdas that are available. Okay? With that, we're done. Thank you.